We are opening the second day of the FisMat today. My name is Giacomo Ghiringhelli. I'm coming from the Politecnico di Milano. And it's my greatest pleasure to introduce today for the plenary lecture Professor G.A.Sawatzky from Vancouver, from the University of British Columbia in Canada. G.A.Sawatzky is a great name in solid-state physics. His activity has been taking place for more than 30 years in the Netherlands, in Groningen, and then some 15 years ago he went back to his original country, which is Canada, taking a position in Vancouver. His name is very much related to several seminal works on spectroscopy and on the classification of a strongly correlated system. I think that everybody knows the Zhang-Rice-Sawatzky-Allen diagram for classifying insulating materials and semiconductors, and the G.A.Sawatzky theory also for spectroscopy. He has been pushing very much the field of electron spectroscopy and X-ray absorption spectroscopy over the years, and I think one of the best contribution of G.A.Sawatzky has been really to enjoy mixing his ideas with everybody and sharing his views with experimentalists and theoreticians with the same enthusiasm, and really I think this is extremely important from the point of view of an experimentalist, because George has taught us how to read our results more than telling us, oh, give me your results, I will give you the interpretation. This is much more effective in spreading the new ideas and the new ways of understanding the experimental results than just working on in separate rooms. So I think that it's really a great pleasure for all of us to be able today to listen to his presentation, and I think we can start welcoming him.
Thank you very much. Okay, well, thank you very much for the invitation to talk at this very nice meeting you have. Well, today I'd like to talk about the issue of whether or not we are really using the right approaches when we leave out in our model Hamiltonians, shall we say, and in our interpretation often of experimental results, if we leave out the oxygen or the anion orbitals specifically. And I will show, actually I'll even match up a little bit with some plenary talk yesterday, which had to do with combining soft condensed matter with hard condensed matter. In other words, we will find that things are actually forming molecular orbitals inside the solid rather than having one electron basis sets which have the full translational symmetry. You know, of course, that it's only the many electron wave function that has to have the full translational symmetry and not the single particle, single electron wave function. And that's where we're sort of going to go. Oh, I got to do it here. Yeah, that's right. Okay, so this is my starting point. We cannot solve a problem exactly. The starting point really matters. And we cannot solve these problems exactly. In the Cuprates, we've been busy for many, many years, 30 years, and we still haven't got a consensus of where that is actually going. And it's very important to have the right starting point, or a starting point that would lead us to the right answer. So for the Nickelates, for example, oops, Oh, I guess this thing does work, right? Aha. Ah, now I know. Yeah. Okay, so for the Nickelates, like neodymium 3+, nickel 3+, O3, formerly Nickelates 3+, but we could start with nickel 3+, which has a D7 ground state, 7d electrons, and actually because of strong covalency, it's a low spin system, so it has a spin of 1/2, and it has 3, oh boy, yeah. It has 3 d-holes in an EG orbital and a full oxygen 2p band. We start that way, and now we start doing some model calculations or things like that, with Hubbard or whatever you like. Okay? Or we can also start with, say, okay, come on, the nickel really doesn't want to be 3+ so badly, so it would rather be 2+. We would have 8p electrons, but that would be a spin of 1, most certainly. And then we would have 1 hole per nickel, but it would be on oxygen, 2p, and this would now be a magnetic spin, a magnetic thing in a metallic host, because I have to take into account that these oxygen p electrons form a metallic-like band. That's a very different starting point. And I will show you that probably that's the right starting point for the Nickelates, and that's not the starting point we have been using generally. I'll get there eventually. By the end of the talk, I'll know how to do this. So after almost 30 years, at least, I am still looking for the correct starting point for the Cuprates. And for the Cuprates, for example, the models and the glue in the Cuprates, well, we have models. There are single-band Hubbard models. You have three-band Hubbard models. You have models which concentrate on the importance of the von Hof singularities. And we have models like Tony Leggett that concentrate on long-range Coulomb interactions rather than the Hubbard short-range ones. The glues that people talk about are magnons or spin fluctuations, phonons. They could even be excitons. These are electronic, polarizable via and polarizability, or they could be plasmons and so on. And the Cuprate family actually does a great job of accommodating all of these. So everybody is happy. Whichever theory you have, it works for something, and generally for something important. So there was grandfather Cuprate, for example. Well, the Cuprate family was having breakfast. And grandfather Cuprate said, hey, I just got a new preprint of a paper that has a really sophisticated, complicated theoretical approach to the Cuprates. And he was talking to his grandson. And he asked his grandson, have you seen that paper? Yes, said his grandson, I've seen it. And I got very excited about it. But now, how can I contort myself into shape so that these people can also be happy with their theory? And this is the Cuprate family story. Okay, so in summary, I'll talk about the basic concepts of electronic structure of transition metal compounds. I'll talk about this charge transfer versus Hubbard, but then I'll go to this so-called negative charge transfer, gap materials, and self-doping, and mixed valence. And these are systems where you have a different starting point than we generally do. Okay? And that's a starting point where you can't really start with simple little clusters. Experimental evidence in high oxidation state transition metal compounds that you have this negative charge transfer gap. I will present with the doped Cuprates, the pure Nickelates, and also the bismuth-pates, which also are perovskite structure, and are superconductors if you dope them with potassium or with lead. Okay? Okay, well, very simply, for those of you who don't know the story, transition metal compounds are generally made out of transition metal and oxygen, or they could be a different cation. This is an example of the Cuprates, for example. And then you have two energy scales. You have two energy scales corresponding to where you take an electron for the charge excitation. Take an electron from here and put it onto another copper. That would mean that you start with coppers, which both have 9d electrons, and then you go ask yourself, how much energy does it cost to go to d8 and d10? Okay, and that would cost you the Hubbard U. That costs you the Hubbard U. you also have another energy scale, which is the charge transfer energy, where you take an electron from oxygen, which had a full oxygen 2p shell, and put it onto a copper, and that's a charge transfer energy. And now you can draw a diagram in which, for example, if the Hubbard U is the lowest energy scale in the excitation of that kind of excitation system, like this, and now I have a chemical potential in the middle here. These are the n-1 particle eigenstates. Those are the n+1 particle eigenstates. So really, you can't draw the ground state in this system. Okay, you never should. The gap here between removal and electron addition would be U. But you can have the oxygen bands in between here, and if the charge transfer energy is less than this Hubbard U, then in fact the lowest energy excitations are charge transfer excitations. And in fact, if you dope this system with holes, the holes will not go into a D band, but will go into an oxygen P band. Those are called charge transfer gap systems. Now, if this charge transfer energy is so small that this overlaps with that, then we have a system where you really get complicated, and those are most of our systems, actually, that are really interesting. Okay? So, we know from X-ray absorption spectroscopy, so this is a picture of the Cuprates. I think you've all seen it very many times, probably, where you have a spin of a half, copper is B9, you have a spin of a half on each copper, they're antiferromagnetically ordered, and now we're looking at, for example, a hole on the oxygen. And how do I know the hole is on the oxygen mainly if I dope the system? Well, X-ray absorption spectroscopy shows me in this system lanthanum 2 X, strontium X, copper 04, that if I had just lanthanum 2 copper 04, the copper would be 2+, would be D9, and now I replace lanthanum with strontium, and I would get some copper 3+. I would get some copper 3+. But actually, X-ray absorption tells you on the oxygen edge that you have this pre-edge peak, which goes up in intensity very, very strongly as I replace the lanthanum with strontium, and that really is a very strong indicator that the holes, when you dope with strontium, that the holes go mainly on oxygen and not on copper. Okay, so that already changes your starting point of the dope system. Let me just go on a little bit. That there were 3 early papers actually in 1988 which all claimed that oxygen will play a central role in the problem. And I want to very quickly go through these 3. The first one is one which just treated the copper as being an impurity in a whole band oxygen lattice. Okay? And doing that, then one can do an exact calculation actually within a Hubbard Hamiltonian, but with all the multiplets, the atomic physics of the 8 states. Those multiplets actually spread out over 12 electron volts. You know, it's not a small energy scale. That's the reason why we have the beauty of Hund's rule and so on and so forth. Okay? So those multiplets would be all over here. So this is the electron removal part from the ground state, which is D9 and a full oxygen band. That was the assumption. Okay? So I look at the electron removal states. All I need to do is solve a 2-particle problem, which basically is the G.A.Sawatzky theory of J spectroscopy, but you could do it exactly. And you can get all of these irreducible representations of the D4H point group for 2D electrons. And then you find out that your multiplets spread out all over the place. Okay? But there is one lowest energy state. That lowest energy state has a spin of 0. It's a low spin state. It's a local spin compensated state. And later on, or actually at the same time, almost overlapping exactly, Zhang and Rice did it in a different way and came up with the Zhang-Rice singlet. And there were 2 other papers at the same time. One of them was that by Emery and Riker, which said that, well, look, the oxygen in this structure is actually between 2 coppers. So it should be equally shared between the 2 coppers. And then they showed that you would actually, this would lead to a 3-spin polaron, and I'll come back to that later. Whereas the Zhang Rice story was that, well, the doped holes go mainly on oxygen, but they form a molecular orbital of the 4 oxygens around a single copper, which they've chosen somehow or other. And that orbital would have x squared minus y squared symmetry about that copper, mixing strongly with the one hole that you have on the copper x squared minus y squared orbital. And that would form a singlet state with a very strong exchange interaction. I'm still not getting there. With a very strong exchange interaction between the copper and the oxygen. That exchange interaction is more than half an electron volt. It's huge. So the story then was that you would form these singlet states with a hole in this linear combination of atomic orbitals that have x squared minus y squared symmetry exchanging with this electron in an x squared minus y squared orbital and forming a singlet state. Now, once you have that and say that, well, this is the right story, then actually you could go back to a single band Hubbard-like model because it looks like that, right? You again made the spin 0 on the copper effectively by adding that extra hole. Now, that story, indeed, there's many people work with single band Hubbard models and with PJ models and so on, and indeed, it gives you a very nice agreement with the measured experimental dispersion that you measure with angular resolve polarization. Okay, so this was, this is actually done in an approximate way. This is in a self-consistent Born type of approximation, but it seems to work very, very well. Okay, now, what really is the importance of the inclusion of the oxygen 2p? Well, a student of mine once came to me and asked me, he was a computational physics student, and he asked me, I'd like to do a PhD in a problem in which I'd like to do a calculation or write the software for a calculation that nobody else could do or has yet done. And he, therefore, chose to do this calculation with a very, very big exact diagonalization type program. And he used, indeed, the Hamiltonian in which you have both oxygen degrees of freedom and copper degrees of freedom, and used on oxygen and also used on coppers, and hopping integrals between them. And hopping integrals between them. The effect of Hamiltonian that you could get if you make this UDD very large, to make it very large, is one that gives you a super exchange between the copper spins. They have a super exchange, antiparomagnetic exchange interaction, and it gives you an effective hopping integral between the oxygen. Really don't, I guess. Hopping integral between the oxygen orbitals here, and it gives you a hopping integral between the oxygen and the copper. And there's one very special term that's very interesting. It's a term, and if I have a hole on the oxygen and a hole on the copper, then the copper hole can hop onto that oxygen, giving you this. And then this oxygen can move on to the copper, giving you this. And now effectively, compared to this, you've hopped this hole into that oxygen, but you flipped its spin and you flipped the copper spin. This is almost a Kondo-like term, but it's a very interesting term and the most important term, actually, in the Hamiltonian. When you do that, and you do this exact calculation with 32 copper sites, which is horrendous. I think the basis set was 10 to the 18th or something like that, which he could reduce down by using certain symmetries and so on. Anyway, you get pretty well the same dispersion as you got with the TJ model. Well, that's very interesting. But the physics of this is completely different. If you now look at the correlation function as to what is the spin correlation between the copper spins here at these vertices here around an oxygen hole, where the oxygen hole, however, is got the full periodic symmetry. It's at pi over 2 in momentum space. But you can calculate that correlation function because he has all the eigenfunctions. Then you find out that these copper spins are very strongly ferromagnetically coupled around that oxygen, right? Whereas they were antiferromagnetic. Yeah, the antiferromagnet for a spin 1/2 antiferromagnet with full quantum fluctuations, you get a spin-spin correlation function of minus 0.33. For a singlet, you would have minus 0.75, and for an EAO antiferromagnet, you'd have minus 0.25, and for a ferromagnet, you'd have plus 0.25. This is plus 0.13, or at a different point in momentum space. Remember, these are periodic, okay? But you can still calculate the correlation function, and that is plus 0.17. So these are huge ferromagnetic-like correlations. This shows strong ferrocorrelations close to the doped hole. This does not look like a Zhang Rice singlet, but actually the spatial hole has x squared minus y squared symmetry nonetheless, because you can make a linear combination of the hole here and the hole there if you are in diagonal k vector here. Okay? And they actually have x squared minus y squared symmetry. So it looks like you have Emery-Rider 3-spin polaron in a Zhang Rice-like symmetry. So they're both right. Okay? And I just drew that picture over here just to show you that symmetry. Now, what is that state? Well, it's a very interesting state. Remember, I started out with 2 copper spins that are strongly antiferromagnetically coupled. I put in an oxygen hole. Let's say it's spin up. But this spin up hole, this oxygen, you would think is in inversion symmetry, right? But it's not, because the spin has a particular choice. As soon as you put a spin there, it's no longer in inversion symmetry. And actually, it would... Very annoying. And actually, it would love to be a little bit closer to this copper, because then it could even have a larger exchange interaction here, and it wants to get away from that repulsive, because this is a very strong antiferromagnetic coupling, much stronger than that. Okay? Oh, thank you. Okay, so actually here, if you started out from this, then you see that from the Heisenberg exchange Hamiltonian, you can have this spin flip down and this spin flip up, right? So that's the other term that you would get, mixed in very strongly because of that very strong exchange interaction. Now, when you're over here, this oxygen is in an inversion symmetry, okay? So it doesn't have a preference, it'll stay in the middle. But now you go to this one, where this spin has flipped back up, but that spin has flipped down, and then the oxygen wants to move that way, because this is a very favorable state. So this is an eigenstate of an n-1 electron system, is a linear combination of these 3 states. Now, it's not quite like that because you are in an antiferromagnetic background, but it's pretty close to that. And it has a strong phonon component, a hole, an oxygen 2p, strongly dressed by a phonon plus 2 magnons. This is the state of a phonon plus 2 magnons dressing this hole. Oh yeah, I can't do that anymore. The eigenstate that of this simple isolated problem, it looks like this. It is actually, it has singlet states or spin up, spin down states for the 2 coppers. This is for the oxygen hole being spin up, and one copper spin up and the other copper spin down. But notice the plus sign. It's a ferro component, a spin triplet phase rather than a singlet phase. Okay? And the net spin is a half, and actually the energy is at -1 times this absolute value of the J. So it's a very large energy scale that stabilizes this particular state. Okay, so let me introduce to you a new cuprate camp, which has only one person in it, that's me, And the new glue is a phonon plus 2 magnons. And now the phonon and magnon people have to get together. Finally, they always have separate conferences, right? They should get together and form this phonon plus 2 magnons. This is an important contributor to the mid-infrared spectroscopy, as was shown by these people in these years between 95 and 2000 or so. And you can actually see these phonons plus 2 magnons. In the undoped material, you have an infrared absorption at about 0.5 eV, which is very, very sharp, and actually corresponds beautifully to a theory of a phonon plus 2 magnon at particular places in the Brillouin zone, most of them at the zone boundaries. You need 2 magnons because in optics, you can't, your net spin and change has to be 0, and you have to have a phonon to compensate for the momentum that you then get, because your total momentum has to be 0 in optics also. And this is the theory here, and the experiment is this. Now actually the much better theory has been done by Theo Cole, who actually showed that you can also get this stuff out over here. But this is a very sharp resonance, which we call a virtual bound state, which actually is a new boson, you might say, and you can treat it as a boson. Okay, so this is all very nice and dandy. Whether or not that's the right picture or not, I don't know. But at least we started with a picture in which we really had holes on oxygen, and then did a very big exact diagonalization that could get us the Zhang Rice singlet state, if that was the correct one, but it didn't. It gave us this composite state. Okay, now in a recent paper, we've also shown that the single particle dispersion, that shows that the same single particle dispersion results even if we neglect the quantum fluctuations in the antiparthenic background. So in the background, the quantum fluctuations are apparently not important, actually. That's what the exact diagonalization and this other calculation show you. This, however, does not mean that spin fluctuations are not important for the pairing, because we've also shown in an exact type of model calculation that even though you may have perfect agreement with the single particle dispersion leaving out the spin fluctuations, these still may be the thing that are the glue that give you pairing. And also another statement, good agreement with experimental single particle spectral function need not mean that one has the right model in general for the Cuprates, because there you have strong pairing type interactions. Okay, now is this oxygen pre-peak that we see in X-ray absorption, which was the thing that told us that maybe we should have a different starting point. Don't think of copper 3+ so much, but think of copper 2+ and a hole on oxygen when you dope the material. Is that an issue only for the Cuprates or also for other materials? Well, let me show you. So here is lithium substituted nickel oxide. You know, this is the battery material, right? So it's a very important material, actually. And lithium substituted nickel oxide, you see very clearly, again, this pre-peak in the oxygen 1s X-ray absorption, 1s to 2p transition, which is only allowed if there's 2p holes. And you see this very, very strong pre-peak. And we demonstrated that, in fact, this material also, the holes do not go on nickel. It is not really nickel 3+. It's actually nickel 2+ and a hole on oxygen. And they are strongly coupled. Going on, so this is Nickelate, lanthanum, nickel O3. Okay, and there also, the lanthanum is 3+. The nickel is also, should also be 3+ if you have 3 oxygens, which are all 2-. Okay? This is for a thin film, actually, grown epitaxially on top of LSAT substrate. And there again, you see this now in a pure material. Okay, so now I'm not doping. I'm now looking at the pure material. And you see this extremely strong narrow pre-peak over here in the oxygen edge. indicating again that the holes are mainly on oxygen. Now, then you have a real problem as to how to describe it. So let's say that we assumed that we had a positive charge transfer gap, a large charge transfer gap, but not as large, larger than the U, smaller than U, okay? So that we could have the charge transfer excitation, the band gap would be determined by this delta prime. I would have the upper Hubbard band, I would have nickel, I would start with D7, so these excitations would be electron addition, 2D8, and these would be electron removal, 2D6, so you would have a U, right? Coulomb interaction. You could think of the other limit over here, where actually this upper Hubbard band has moved down below far enough that you've added one more electron to it, so that the ground state would be D8, and these electron removal states here would be D8 to D7, and these would be D8 to D9. But now, for charge compensation, I have to have holes in the oxygen band. And you can have this intermediate case, which is extremely interesting. As a matter of fact, I claim that this is the case also for samarium hexaboride, where you have a mixed valent ground state, and you can get it beautifully in this kind of a picture, in which you have where the valence is someplace between D7 and D8, but the low energy scale, in the low energy scale, I can only add electrons to those nickels that are D7, and I can only remove electrons from those nickels that are D8 if I want to stay in the low energy scale. Okay, now, we believe that the Nickelates are sort of over here, which actually is, in a sense, a negative charge transfer gap, where now we define the charge transfer gap as being this delta prime. Now, I said already, if we cannot solve a problem exactly, the starting point really matters, and I've gone through all of this, rather than having nickel 3+, I would take nickel 2+, would be D8 with a spin of 1, and 1 hole per nickel would be in an oxygen 2p band. Now, the Nickelates have a very, very rich phase diagram. Jerry Torrance did this many years ago, where depending on which rare earth you have, which has to do with the size of the rare earth ion, you have semiconductor metal transitions and insulator to antiferromagnetic transitions. For example, here you would go from a metal to a semiconductor or an insulator and to an antiferromagnet over here. Now, these are materials now that are being studied very much, because now with epitaxial growth we can finally get single crystals. We couldn't get single crystals of these materials, and therefore it never was quite sure as to what was going on. Now, with epitaxial growth, we can have single crystals, and with the new X-ray reflectometry and resonant inelastic X-ray scattering, we have the tools that can actually look at a thin film, epitaxial thin film, with a lot of signal. Okay. So there's a lot of things that actually came together. And recent resonant inelastic X-ray spectroscopy point indeed very strongly to a negative charge transfer gap system for the Nickelates. These are the people from Switzerland that actually did those experiments. These are the people that made the materials, Tristone's group, and of course Schmidt here from the Swiss Light Source. Now, their data showed the following. We saw the X-ray absorption spectrum on the nickel edge now, the nickel 2p to 3d transition, looks like this. Okay? And this is, 850 electron volts here in this ring. So, and we always thought that this two-peak structure and stuff like that was because of the multiplet structure that you have with one hole in a 4 2p and a 3d8 like final state, because you've moved that electron up to the d shell. Well, and many people tried. Everybody in the field used little clusters to try to calculate the spectrum, and nobody could actually get it right. And they assumed, or actually, there are many papers published that claim that they did get it right, but when you look carefully, they did not get it anywhere near to being right. So what this this resonant inelastic X-ray scattering experiment does is it looks at the excitations of this system. And the excitations of this system as a function of where you are in energy in this intermediate state. If it was only multiplets that you were seeing, then you should you should see all these very sharp little peaks over here, and they should be independent of the incoming energy. Now what you see is that as long as you are in this part of the spectrum, they are independent. Yeah, the red one, the blue one, the purple one. But as soon as you go into here, zoop, it just disperses out with energy. Meaning, those are completely different states. Those are the states that are the continuum states corresponding to the oxygen 2p band that we had neglected in that, at least we had neglected that there were holes in there in that, in the theories that were being used. Okay, this is a very important experiment. And showing it in another way, over here, so this is at 15 degrees Kelvin, so this is in the insulating phase. So this is on a thin epitaxial film. And you see that here is that continuum, right? And here is that blob which is independent of this energy. Intensities vary, but not the energy, okay? And this is that continuum. That's in the other region, in this region of the absorption spectrum. This is in the insulating phase, and you see clearly that there is a gap. Yeah, there's a gap in here. Now you go to the metallic phase, and that gap closes, and those continuum states extend all the way down to zero energy. Now that's hard to see because you know that your oscillator strength goes to zero when you're down there anyway for charge excitation. Okay? So, but still, this really goes all the way down. So these lowest energy states, these metallic states, are states which involve oxygen 2p holes, actually. Now, how does that work? Well, if you have a high oxidation state transition metal compound, generally we expect the transfer energy to strongly decrease for higher oxidation states. This could mean that we should have different starting points. I've already told you all this, okay? And this here also. The charge degrees of freedom would then be on oxygen 2p bands. Now, what we would then have is we would have a high density of large U nickel 2+ states with strong hybridization and exchange with the holes on oxygen. It's an Anderson lattice problem, but with a hybridization which is much too large for a Schrieffer-Wolff transformation, so it would not be a Kondo-like problem. But also for Kondo, we would have a Nozière exhaustion principle. Because, remember, that if the nickel is in a D8 state and it has a spin of 1, but it has only given 1 electron to, or 1 hole to the oxygen band, there's not enough there to screen all of those nickel spins. Would likely remain metallic as lanthanum nickel 03, a bad metal, unless we include strong electron-phonon interaction, and that's where I'll come to now, in that hopping interval. So this is really what seems to be happening. So consider, remember, nickel 03 as nickel 2+ with a hole on oxygen. Okay, let's take the other extreme limit, or starting point. Then each nickel is surrounded by an average of 2 oxygen holes in an octahedron, because each nickel has an octahedron of oxygen. And if I have 1 oxygen hole per nickel, that means I have 1 hole per 3 oxygens. That means I have 2 holes per 6 oxygens. And I'm going to put them into a bipolaron. Okay? And what they will want to do is, if you can't have 2 holes on this octahedron and also on that octahedron bonding strongly with a sigma bond to the center. So what happens is that you get collapsed octahedra, in which this bond is very, very strong with all of these holes in a molecular orbital, but now of octahedral symmetry rather than this square planar square symmetry in the Cuprates. And this bond length is very large, so that this nickel oxygen distance is very large, and that covalency is much smaller. The nickel is 2 plus with spin 1, the nickel is 2 plus with spin 1, but now very strongly covalently mixed over here. Okay, let's see if that actually can work with a theory. Actually, I should say that we know that there's a phase transition. The semiconductor metal phase transition is a transition in which you get this doubling of the unit cell, or you have this half superlattice structure, which corresponds exactly to these compressed and elongated octahedra. So doing a calculation of exact diagonalization and Hartley-Fox, Steve Johnson was the main guy who did this, we showed that it's not really charge disproportionation that is occurring, it's bond disproportionation, where you get these short bonds and you get these long bonds, exaggerated a bit in this picture, where the nickels all have a spin of 1, and the oxygens poles, they actually also couple to a spin of 1, but then couple antiperpendicularly to the nickel spin 1, giving you a spin of 0. This, we believe, is the picture that one should probably use. And you see, indeed, that if I make this bond disproportionation, increase this difference in bond length, then at about 0.05 angstroms difference, I start getting a gap in the spectral function, giving you an insulating-like state. But it's a very different insulating-like state than you would get from a model in which you would assume you had charge disproportionation. Now, what about, does this have anything to do with this other very beautiful system, the barium or strontium bismuth-O3, which I said before, if you replace the bismuth with the strontium or barium with potassium, that you actually get a superconductor and a pretty high temperature superconductor. Now these materials have nothing to do really with strong correlation. They're weakly correlated, they're not magnetic. People say that there is charge disproportionation, but is that really true? That the bismuth 4 plus in this case would disproportionate into 5 plus and 3 plus? Well, bismuth 4 plus has 1 electron in a 6s orbital. This is a very orbital, very extended with lots of nodes, right? The bigger your main quantum number, the more nodes you have in your radial wave function. And how about electron-phonon coupling? Is that the mechanism for superconductivity here? And in the end, is this perhaps similar to the Nickelates? Well, I think it is. But in a way also very different. If I look at the oxygen band structure, and I've just drawn a schematic, then the states that have E.g. x squared minus y squared with z squared symmetry about a central nickel or bismuth atom, they would be up over here. The Fermi energy would be here. So they would cost me little energy to move them out and empty them. That's what happens in the Nickelates. Okay? Here, though, are the s orbitals, the A1G symmetry states, which the combination of oxygen states, which would mix with that 6s orbital of bismuth. Okay, so let's see what happens. Well, actually, this is already the band structure calculation. We shouldn't have much of a problem of correlation. But the 6s band is here at minus 10 electron volts. It's got piles of dispersion. But actually, all of that dispersion comes because of the hybridization with oxygen, and not because of bismuth-bismuth mixing. And these states that were down at the bottom, the A1G states and oxygen that were at the bottom of the oxygen band, zoop, get pushed up above the Fermi energy, and there are your holes. These are oxygen holes of linear combinations of A1G symmetry, which get pushed up over there because of strong hybridization, and the 6s of bismuth gets pushed down over here. And notice how narrow that band is. It's suddenly has become a very narrow band, actually. And you got to be careful with this, because the U on oxygen is 4 electron volts. It has been measured with Auger spectroscopy, so it's not negligible at all compared to this band. So maybe there is a correlation problem in the end. Who knows? Anyway, this is a very narrow band. There is a gap formed over here, but that only occurs if indeed you have, again, this bond disproportionation. Long bond lengths and short bond lengths alternating. And that is the right structure for the barium and strontium bismuth O3. So, in a sense, this is actually a little bit similar to the nickel story. You start out, so this is just throwing out the barium and the bismuth, or the strontium and the bismuth, and just looking at the oxygen band structure you would get. Okay, and then this would be the symmetry projected A1G symmetry states. Notice they're all down here at the bottom of the band. Yeah, chemical potential is here. Right, that's what I said before. Now you put in the disproportionation, yeah, the shorter and longer bond lengths, and you put in the tilting of the octahedra, and suddenly you get something rather narrow over here. And then, when you switch on the hybridization, this is still the zero hybridization with the bismuth states were down here. If you switch on the hybridization with the bismuth, you get the bismuth states move way down in energy, down to 10 electron volts here, and we were up at 4 electron volts here, down to 10 electron volts here, and an oxygen A1G symmetry state gets pushed out over here. This is a molecular orbital of an octahedron of oxygens with sigma bonding oxygen p orbitals. Okay, so there is a link between all of these materials, and the link actually also is, by the way, I should have said, again, I should have said that in there are exactly 2 holes per oxygen octahedron in that empty state. That's why you have a gap. These are bipolaron. These are 2 holes in an oxygen octahedron, but these are bipolarons which have crystallized out in a charge density wave, or whatever you want to call it. It becomes a molecular density wave, actually, in this crystal. Okay. Now, what you have to do to get rid, or to get, and this is the competing phase for superconductivity. What you have to do is get rid of that order, just like you have to get rid of the magnetic order in the Cuprates in order to get superconductivity. And in many cases, you have these competing orders. You have to get rid of the one that competes with the superconductivity in order to get superconductivity. And somehow or other, and we don't know exactly how that works, but somehow or other, this is done by potassium substitution. And when you substitute potassium, you start emptying up this band here. Yeah, also a sharp band, just below the Fermi energy. That is the band which corresponds to the EG symmetry orbital of oxygen states. And somehow or other, with sufficient doping, that changes the whole story and gives you into, but I think still bipolaron-like concept still probably holds, and that you really have a kind of a bipolaron-like Bose-Einstein condensate or something for the superconductivity in this system. Okay, I'm finished. Thank you very much. Oh, my chairman is over there. Is my time not up?
Yes.
Well, maybe we can have a discussion. No, I think, well, I'll go through the summary very quickly. So, oxides with formally high oxidation state elements can be negative charge transfer systems. Now, you have to be careful with that statement. That is true for the late transition metal and 3Ds, right? Not for the early ones. So, titanium can be 4+ like or behave like 4+, although it will be very strongly covalent, and we know that it is. The mobile charge degrees of freedom are then in mainly oxygen 2p bands. The O2p whole states in the low temperature phase form molecular orbitals. These are squares of x squared minus y squared symmetry in cuprates, and octahedra in cubic perovskites. And these holes in the octahedra, you then have to think of that as being a new element, you might say, and that has periodicity, which you will then give you a band structure, but that's why those band widths are so narrow. Okay, the width of this large object actually, which has only a few lengths, or one length in each direction. The Nickelates, in the Nickelates, the lowest energy oxygen 2p hole states are of EG symmetry, x squared minus y squared, and 3z squared minus r squared. There's a rather interesting little sum that you can do, and I think I have an extra slide. Here it is. There's a little sum that you can do if you have an octahedron of oxygen p orbitals, and you just have hopping intervals between them, and you put in 100 U on those oxygen orbitals. These are all the various symmetry orbitals that I could form. You can do an exact diagonalization of that little model. If you had only one hole in those orbitals, then you would have the lowest energy state for the hole would be EG symmetry, as I already told you. And the highest energy would be in A1G symmetry, and there's all kinds of T1Us and so on in between and so forth. If I had, rather than holes, if I had electrons, then this would turn around. Okay, the A1G would be the lowest energy state. Okay, that's where the business success comes in. But if I take and put two holes into this octahedron, then I have the possibility of forming a triplet, because the lowest energy state was an EG state, so I can have one hole in x squared minus y squared and the other hole in 3z squared minus r squared. And it could form a triplet. And look at what happens if you do an exact diagonalization. This is just the one hole case, so the electron case. In the electron case, you just stay a singlet. In the hole case, you find that you very quickly, even just a very small U, will very quickly switch you into a very strongly stabilized triplet state. Okay? This is a triplet state, a very strongly stabilized triplet state. That is why I say that these two holes in an EG state of oxygen molecular orbitals actually have a very strong triplet stabilization. That is not because of exchange. That's because of the fact that they are fermions and the fact that they are, that the U doesn't want two electrons or holes to be on the same site. There's some very simple little calculations you can do to prove to yourself that you can have very strong energy differences with spin states in a finite system like that, just because of kinetic energy terms. Okay. So I wanted to go back to here. So in the Nickelates, the lowest energy has that. In the bismuth case, they are of A1G symmetry. And in the Cuprates, they again are of EG symmetry. However, the Zhang Rice singlet I've shown, or the single band, may not be applicable in the Cuprates. That you really should take into account these oxygen states explicitly. And then you get this ferromagnetic coupling between the copper spins that move along with the oxygen, but are in a triplet state. And you have this phonon plus two magnon-like dressing. The semiconductor metal transition in bismuth and nickel systems are similar, resulting in a breathing-like polaron mode which condenses into a bond disproportionated ground state. In the bismuth, this competes with a potential superconducting state because of the strong attractive interaction between the two O2P holes in the collapsed octahedron. Attractive because of the common coupling to the bismuth. If we can get rid of the spatial ordering, we should expect to get high superconductors. No, I really am. Thank you.
Well, thank you very much. We started late, but I think we have the time for one or two questions from the audience. Carlo?
Yeah. George, I really appreciated your talk, but I would like to make a comment.
Good.
That,
Would you like the microphone?
oh,
You can use this one.
I think they can hear. I think we have to have a different attitude if we want to study the specific property of the system, or if we want to study the general properties like competing orders and phase diagrams. And I can show you, I can mention one example. Until the 60s, the superfluids, superconductivity and superfluid helium were studied mainly for their specific properties. Then, since then, we have to mainly consider the general aspect which were included in the general framework of phase transition, for instance. And taking this attitude, of course, one has to look for a proper coarse graining. Now, all you have shown to us was to look into the specific problems related to the actual local properties of the system. And I believe that has to be studied before getting to the second step. However, and you have shown how complicated is the coarse graining in this system. However, I feel that looking at, if you, for instance, consider one-band Hubbard model or three-band Hubbard model, we have been considering both cases, and as far as the general properties of the phase diagram and competing orders, they usually lead to the same, exactly the same result. Or if you have phonons like to help the strongly correlated system, or you put charge transfer, excitonic-like mechanism, you get exactly the same thing. So, as far as the general properties. So that is the way that I consider we should really go into to simplify this scheme. Otherwise, we will never get out of the problem of ITC superconductivity. Thank you.
To a large extent, I agree with you, but to a certain extent, I also don't. And the problem is that I think you and I both agree that there is no, as yet, solution for the high TCs. Now, whether you mean by that the actual transition temperature and the details of the phase diagram, or whether you mean by that the generic, general-like model like the Hubbard model, which in fact may give you superconductivity. In fact, Stevenson claims that you can show for small u that it does give you superconductivity. But that is not sufficient for if you want to have an understanding of what kind of materials really we should be looking for, and what are the main drivers of the low energy scale electronic structure. Therefore, I think that both things are important. It's really important to look at the models and to, I'm sure you agree.
That is the factor to go to the second step, actually.
Yeah. No, that's right. So I say that I think that in the models that people have studied up to now, the ones you mentioned, either the three-band Hubbard model or the single-band Hubbard model, for example, they never did put in properly this exchange interaction between the copper and the oxygen in a sufficient way that would give you this ferromagnetic coupling. I've never seen that. And yet it comes out automatically in this, and that's a very big coupling. So that really must influence how you should interpret your experimental results also. So I think we actually agree. Both camps are, it's very important to have exactly solvable models, although even those aren't exactly solvable. And it's also very important to really understand what the combination, or what the relevance is for the particular materials that we are actually studying.
Okay, just a very quick question. At some point in the copper oxides, when you increase the doping, the system should become more conventional metal. So in your opinion, at which doping you have a transition from a picture described by these molecular states to a picture which is more conventional?
Well, that's a very, very good question. And you know very well that the stuff that I showed on the exact diagonalization was for, you know, a single hole or two holes in the system. So this is in the very, very, very dilute doping range. And what happens as a function of doping, I think it's much more complicated, because I cannot imagine that at a doping of 20% or something like that, that this picture of that you get from the single hole still is valid. These things are now strongly overlapping each other, and they cannot possibly exist in a simple as a simple extension. So I think the picture really changes as a function of doping. Now, whether that happens before the end, probably, I would say that the picture probably changes, shall we say, at maximum TC or something like that, the optimal doping, and then you start getting away from that, and then eventually you get to something that is a very strongly, that is more like the band structure approach, which is more in this mixed valent-like regime that I showed, which is this very strong hybridization between copper and oxygen that band theory actually gives you. Their wave functions are 50-50, copper and oxygen, right?
Coming to your to the case of bipolarities in bismuth compound, you should observe in a normal phase the signature of bipolaron formation and preformed local pair.
Sorry?
So, what do you think about the normal phase in the bismuth compound? You tell us that there should be bipolaron there.
Yeah.
So they should be seen in the normal phase also.
Yeah, but they do. So in the undoped material, just the pure barium bismuth O3, it does have this half superlattice structure, which has these compressed and elongated octahedron. And from X-ray absorption, you see that there is this very strong pre-peak in the oxygen edge again. And what we get from the band theory is that there are two holes in that octahedron. Those projections we did of the band, the band just above the Fermi energy, the colored plots were projected densities of states. And the projected density, the projections we did, was on an A1G symmetry molecular orbital, a linear combination of oxygen orbitals in the octahedron. And almost all of your density is of that character in those whole states. And there are two holes in there. So it really looks like a bipolaron, but they are crystallized, we might say, in a lattice. That's the idea.
Okay, and it's impossible to observe a liquid of bipolaron by increasing the...
Well, I mean, that would be the superconducting state, right? and maybe the potassium substitution or the lead substitution or things like that, maybe that's what they do. They liberate these bipolarons. Then you would have a Bose-Einstein condensate-like problem. But I don't know whether that's the case.
Okay, I think it's time for moving to the parallel session, and let's thank G.A.Sawatzky again for this lecture.